Here we are again. We have Pre-Calc Lesson 88, Exponential Functions, Growth and Decay. If you were just interested, there are a few places where this is applicable in the real world. I know people always ask that. An exponential growth function would be the growth of bacteria, or decay could be radioactive decay in physics. We could have the growth of money, or we could have the voltage across capacitor. All of these things come from this lesson. So the general form is a sub t equals a naught e to the kt. Our independent variable is t. And in it we have, this case, negative values. They have no meaning because we are talking about only growth. Okay, our dependent variable is a sub t. So you can think of this independent typically relates to our x. In this case, it's time. Our dependent variable is the y, or a sub t. A sub 0 is a constant. And it is the value when t equals 0. It's our initial value. Okay, and k is also a constant. Okay, now exponential growth looks like this. This is at a naught. This is growth. And exponential decay looks like this. Okay, and these are two-step problems where the first is solve for k, and we solve for k by taking the log of both sides. And our second step is we evaluate or solve. And in this case, it really just depends on what the question is asking of you. Okay, so I can turn my page. Example 1. So these are very lengthy problems. I'm not going to write out the whole thing, but I am going to reference it. This is referenced to example 88.1. And it says the number of bacteria present at noon, so I'm going to abbreviate. At noon, there was 400 bacteria. Okay, and 9 hours later, the bacteria numbered 800. Assume exponential growth and find the number of bacteria present at noon the next day. So at noon next day, how much bacteria? Okay, so the first thing we do is our formulas. A sub t is a naught e to the kt. And in this case, okay, we are talking about noon. That's our beginning, which tells me that a naught is 400. So I have a sub t equals 400 e to the kt. Okay. Now I'm going to plug in my next value. 9 hours later, I have 800 bacteria. So 800 bacteria goes over here, equals 400 e to the k times my time is 9. Okay. Now I'm going to first, before I take the log, divide everything by 400. So I get 2 equals e to the 9k. And now I'm going to take the natural log of both sides. So I get the natural log of 2 equals 9k times the natural log of e. We know that the natural log of e is 1. So I get the natural log of 2 is 9k. So k is the natural log of 2 over 9, which is approximately 0.077. So my equation is a sub t equals 400 e to the 0.077 t. This is a part of your solution. You do need to have your equation boxed. This is very important. Now it says we want to know what's happening at 12 the next day. So I want to know A sub 24 because it's a full 24 hours from when we first started. And equals 400 E to the 0.077 times 24. Which gives me, this is just a calculator problem, approximately 2,539 bacteria. In this case, I have rounded to the nearest bacteria. Okay? All we're doing is we're using the equation. All right, let's do a second example.
Michael Van Bree to the front desk. Michael Van Bree to the front desk.
Okay, the number of bacteria present at the beginning of the experiment was 1,200. After 100 hours, there were 2,700 bacteria present. We assume exponential growth, so A sub t is A naught e to the kt. And we want to know, it says, find the time required for the number of bacteria to increase to 30,000. Sketch the curve. Okay, so we know that A naught is 1,200. So I will have A sub t is 1,200 e to the kt. And I'm going to plug in this point here. So I will get 2,700 equals 1,200 e to the k times 100. Divide everything by 1,200, leaving me with 2.25 equals e to the 100k. And now I take the natural log of both sides, leaving me with the natural log of 2.25 equals 100k times the natural log of e, which we know is 1. So k is the natural log of 2.25 divided by 100, leaving me with approximately 0.008. So my equation is A sub t equals 1,200 e to the 0.008 t. Now it says find the time required for the number of bacteria to increase to 30,000. So I plug in 30,000 for A sub t, and I'm going to solve for t. If ever my variable is in the exponent, that's when you take the log or natural log of both sides. So I'm going to divide everything by 1,200, leaving me with 25 equals e to the 0.008 t. And I take the natural log, leaving me with the natural log of 25 is 0.008 t, natural log of e, which is 1. So t is the natural log of 25 divided by 0.008, which is approximately 396.92 hours. Don't forget your units. Units, super, super, super important. All right, let's do kind of a different type of problem. Example 3, the amount of substance initially present was 400 grams, and after 90 hours, only 380 grams remained. Assume exponential decrease, okay, which means that might change our formula, and it will, but I will show you what that looks like.
Christian George to the front desk, please. Christian George to the front desk.
We're going to keep it like this. This is still the formula we use to plug in. It's just going to look differently when we solve for k. And the problem says determine the half-life of the substance.
I need Susan McDonald to the front desk, please. Susan McDonald to the front desk. Bye.
So I'm going to plug in my initial value. I'm sorry for all the intercom announcements. Okay, and then I'm going to plug in this point. I still want to solve for k. So I get 380 is 400 e to the 90k. Divide everything by 400, so I get 0.95 is e to the 90k. I take the natural log of both sides, so I have the natural log of 0.95 equals 90k times the natural log of e, which is 1. So k is the natural log of 0.95 divided by 90, which gives me approximately negative 0.00057. Exponential decay has a negative k. Oh, I just realized we didn't sketch the curve. I'll sketch that for you real quick. This is what the curve will look like. This is a sub t, this is t. At 0, our initial value was 400. There we go. There's our curve. Sorry, I forgot that. Back to this problem. K is negative when we have exponential decay. So when I plug it into my formula, I will have 400 e to the negative 0.00057 t. That's my formula. Now, half-life. Whenever you solve for half-life, you take your initial value and you have it, which in this case is 200, and I'm looking for the time it will take, I'm looking for the t to give me that half value of 200. Okay? So, again, we solve it the regular way now, so I get 1/2 equals e to the negative 0.00057 t. Take the natural log. So I get the natural log of 0.5 is negative 0.00057 t, natural log of e, which is 1. And I solve this for t, and I get t is approximately 1,1215.79 hours, and I don't forget my units. Okay? All right, let's do just one more example. Example 4, a radioactive substance decays exponentially. So here is our formula. After 100 years, 500 grams is left, and after 200 years, 300 grams remains. Find the initial and find the half-life. Okay, so I first need to write two equations. So my first one, I'm going to say 500 equals a naught e to the 100t. And then I get 300 is a naught e to the 200t. Okay. And what I'm going to do is I'm going to solve both of these for, sorry, this should be k. Silly, not t, k. I need to solve both of these to find my initial value. Okay, so I'm going to do 300 divided by 500, which 300 equals a naught e to the 200k over a naught e to the 100k. And my initial value cancels here. 300 divided by 500 gives me 0.6. And if I have two things of the same base being subtracted, I subtract their powers, leaving me with e to the 100k. So I'm going to solve for k. Take the natural log of both sides, leaving me with the natural log of 0.6 equals 100k, natural log of e, which is 1. So k is approximately negative 0.005. I can plug in k into one of these equations to solve for a naught. So 500 equals a naught e to the 100 times negative 0.005. This value here is just a number that I can divide by to get a naught. And I get that a naught is 824.36 grams. So my equation, a sub t, is 824.36 e to the negative 0.005 t. Now I need to find my half-life. So I will have a half of 824.36 equals 824.36 e to the negative 0.005 t. I'm solving for t. Now this cancels on both sides. leaving me with 1/2 equals e to the negative 0.005t. And I take the natural log of both sides. And I get the natural log of 1/2 equals negative 0.005t, natural log of e, which is 1. And we solve for t, which is 138.63 years. You do need to memorize this formula for exponential growth and decay. Very, very important. It will not be given to you. But what will be given to you is the end of this lesson. So goodbye.